Imagine a world where the barrier between Windows and Linux dissolves, not with a bulky virtual machine, but with a single, invisible bridge that lets every legacy program, every corporate critical tool, hum flawlessly on an open-source operating system. What if the countless, "I wish it worked on Linux, please," could finally be answered with a simple command line, without sacrificing performance or stability? This is the promise that has driven a quiet revolution for more than 3 decades, a quest that began in the early 90s and has now reached a tipping point. The story starts in 1993, when a small group of developers, frustrated by the dominance of a single proprietary platform, launched a project they called Wine, an acronym that originally meant Windows on Linux. Their vision was audacious: to translate the complex Windows API calls into native Linux system calls, effectively allowing Windows binaries to run as if they were native Linux applications. In a modest email to a mailing list, the founder declared, "We aim to make Windows software run on Unix-like systems without emulation." That single sentence captured a paradigm shift that would echo through the next 30 years. Yet the path was anything but smooth. The early versions of Wine faced a binary compatibility paradox. Windows programs expect a tightly coupled ecosystem of DLLs, registry entries, and hardware drivers, while Linux offered a fundamentally different kernel interface. Translating system calls required a deep understanding of both operating systems, and each new Windows release introduced fresh APIs that broke existing translations. The result was a patchwork of workarounds, a labyrinth of staging patches that lived on the edge of stability, and a community that grew more determined with each setback. By 2008, Wine had reached its first major milestone with the release of version 1.0. It could run classic games and simple productivity tools, but the modern Windows applications that businesses relied on remained out of reach. The community responded by creating a separate branch called Wine Staging, a repository for experimental patches that pushed the envelope without destabilizing the mainline code. These staging patches introduced support for newer DirectX versions, improved handling of multi-threaded applications, and laid the groundwork for what would later become a true universal compatibility layer. Fast forward to 2018, when a company known for its gaming platform decided to take the reins of this long-standing challenge. Valve introduced Proton, a fork of Wine specifically tuned for Steam Play, with the bold declaration that gaming should be platform agnostic. Proton bundled a suite of translation layers, most notably DXVK, which converts DirectX calls into Vulkan, a cross-platform graphics API. This breakthrough closed the graphics performance gap that had long plagued Linux gamers, allowing titles once thought impossible to run at native speeds. But Valve's official builds, while impressive, were only the beginning. A community of passionate developers, led by a figure known as Glorious Eggroll, began to push Proton even further, creating a fork that incorporated the latest experimental patches from Wine Staging, the newest versions of DXVK, and additional tools like F-Audio for audio translation and VKD3D for DirectX 12 support. This community-driven version, often referred to as Proton GE, became the de facto standard for users who demanded the very latest compatibility fixes, even before they were merged upstream. The technical breakthroughs achieved by this collective effort are nothing short of revolutionary. By translating DirectX 11 and 12 calls through Vulkan, they eliminated the need for a Windows graphics driver, a component that had previously been a major obstacle. By integrating F-Audio, they resolved the notorious audio latency issues that plagued early Wine attempts, delivering crystal-clear sound for both games and professional audio applications. And by continuously merging staging patches, they kept pace with every new Windows update, ensuring that the compatibility layer remained relevant in a rapidly evolving ecosystem. If you've ever wrestled with a Windows-only program on Linux, you know the frustration of endless dependency errors and performance bottlenecks. This is where the current tool, the latest build of Proton GE, built on top of Wine Staging, shines. It offers a unified, constantly updated package that can be installed with a single command, after which the user can launch any Windows executable as if it were a native Linux binary. No virtual machine, no dual boot, just a seamless bridge that translates calls in real time, preserving both speed and stability. What makes this achievement truly remarkable is the collaborative model behind it. Developers from around the globe contribute patches, test builds on a myriad of hardware configurations, and share their findings on public forums. This meritocratic approach ensures that the most effective solutions rise to the top, while also fostering a sense of ownership among users who see their feedback directly influence the codebase. It is a living example of open-source innovation driving a disruptive technology forward. Now, consider the implications for three distinct audiences. For gamers, the ability to run the latest titles without a Windows license expands the accessible market and reduces costs. For enterprises, legacy Windows applications that once required costly virtualization can now be migrated to lean, secure Linux servers, cutting licensing fees and improving security posture. And for developers, the existence of a robust compatibility layer means they can target a broader audience without maintaining separate codebases, accelerating time to market. At this point, you might be wondering how to get started with this tool, or whether it truly lives up to the hype. The answer lies in a simple experiment. Install the latest Proton GE build, pick a Windows application you use daily, and watch it launch as if it were built for Linux. The community provides detailed guides, and the installation process has been streamlined to the point where even newcomers can follow along without a steep learning curve. If this is blowing your mind, hit that subscribe button and let's keep exploring together, because the journey doesn't end here. What do you think about the possibility of a truly universal operating system? Share your thoughts in the comments. I'm eager to hear which Windows apps you'd love to see run flawlessly on Linux. And so the experiment begins. You download the most recent build from the official repository, verify the checksum with a trusted GAUPG key, and unpack the archive into a dedicated directory. The installer script, written in Python, walks you through a series of prompts. Do you wish to enable experimental patches? Do you prefer a minimal footprint? Or do you want to activate the full suite of graphics translators? Each choice is presented with a concise description, allowing even a newcomer to make an informed decision without feeling overwhelmed. Once the binaries are in place, the next step is to configure the environment variables that tell the compatibility layer which version of the Windows runtime to emulate. A simple export command sets the wine prefix, creating an isolated virtual Windows file system where all the necessary DLL libraries will reside. The first time you launch a Windows executable, the system will automatically download the required components from the open-source runtime repository, caching them for future use. This process, invisible to the user, is a testament to how far the project has come from its early days of manual DLL placement and painstaking configuration files. Now, let us examine the performance. Benchmarks conducted by independent researchers reveal that the overhead introduced by the translation layer is typically measured in single-digit percentages for most Office productivity suites, and remains well within acceptable limits for graphically intensive titles when the Vulkan backend is engaged. In head-to-head comparisons, a popular first-person shooter running through the compatibility layer achieved frame rates within 10% of its native Windows counterpart on comparable hardware. These numbers are not merely academic. They demonstrate that the tool has matured to a point where it can serve as a viable alternative to traditional virtualization, especially in environments where resource efficiency is paramount. Beyond raw speed, stability has been a focal point of recent development cycles. The community has introduced a sophisticated crash reporting framework that captures stack traces, logs system calls, and uploads anonymized data to a central analysis hub. This feedback loop enables maintainers to prioritize the most disruptive bugs, delivering hotfixes at a cadence that rivals commercial vendors. Moreover, the integration of a sandboxing module, built upon the modern Linux security modules, isolates each Windows application in its own namespace, mitigating the risk of privilege escalation and ensuring that a misbehaving program cannot compromise the host system. The story would be incomplete without acknowledging the human element that fuels this progress. Across continents, from a modest apartment in a bustling Asian metropolis to a well-equipped lab in a European research institute, contributors gather in virtual rooms, reviewing pull requests, debating implementation strategies, and mentoring newcomers. Their collaborative ethos is visible in the transparent development roadmap, where milestones such as full DirectX 12 support and native audio latency reduction are openly discussed and tracked. This openness not only accelerates innovation, but also invites enterprises to adopt the solution with confidence, knowing that the codebase is subject to continuous peer review. Speaking of enterprises, let us consider a realistic deployment scenario. A mid-sized company, reliant on a legacy accounting suite that has not been updated in over a decade, faces the costly prospect of maintaining a fleet of Windows machines. By transitioning to a lean Linux distribution and running the accounting software through the compatibility layer, the organization can consolidate hardware, reduce power consumption, and eliminate Windows licensing fees. The migration process involves creating a standardized wine prefix, distributing it via a configuration management tool, and performing a handful of validation tests to ensure data integrity. Within weeks, the IT department reports a noticeable decrease in support tickets related to software crashes, and the finance team enjoys a smoother user experience without the need for a separate virtual machine host. Gamers, too, reap tangible benefits. The integration of the direct-to-Vulkan translator, coupled with the latest shader cache optimizations, allows titles that previously required a Windows operating system to run on modest laptops equipped with integrated graphics. Community members have compiled extensive compatibility databases, rating each game on a scale that reflects launch stability, graphical fidelity, and input latency. These databases empower players to make informed choices, reducing frustration and fostering a vibrant ecosystem where feedback directly influences future development priorities. What lies ahead for this remarkable tool? The roadmap points towards several ambitious goals. First, a full implementation of the next-generation Direct12 interface, promising even closer parity with native Windows performance. Second, the introduction of a just-in-time recompilation engine that can translate x86-64 instructions to ARM64 on the fly, opening the door for seamless operation on the increasingly popular ARM-based devices. Third, an enhanced user interface layer that abstracts the underlying complexity, presenting a graphical configuration wizard akin to popular commercial virtualization suites, but without the associated licensing burden. These forward-looking initiatives are not without challenges. Translating the intricate semantics of the Windows kernel into the Linux kernel's scheduling and memory management paradigms demands deep expertise and rigorous testing. Moreover, as the tool expands its scope, maintaining a lean codebase while integrating cutting-edge features becomes a delicate balancing act. Yet, history has shown that the community's meritocratic model is adept at navigating such complexities, rewarding contributions that offer elegant solutions over those that merely add bulk. In the meantime, you can become part of this evolving narrative. By contributing a test report for a program you have run, by submitting a patch that refines a specific API translation, or simply by sharing your success story on social media, you help shape the future of cross-platform compatibility. Every piece of feedback, no matter how small, is a brick in the foundation of a truly universal operating environment. To summarize, the tool we have explored today represents a convergence of decades of engineering ingenuity, community collaboration, and strategic vision. It dismantles the long-standing barrier between Windows and Linux, offering a seamless bridge that preserves performance, ensures stability, and empowers users across the spectrum, from gamers chasing the latest release, to enterprises safeguarding legacy workflows, to developers seeking broader reach. The journey from the humble beginnings of the early Wine project to the sophisticated, community-driven builds of today illustrates how open-source innovation can redefine what is possible in the computing world. If you found this deep dive enlightening, consider supporting the channel by sharing the video with fellow enthusiasts who might benefit from this knowledge. Your engagement fuels the research and storytelling that bring these technological milestones to light. And, as always, I invite you to continue the conversation below. What Windows applications have you successfully run on Linux using this tool, and what challenges did you encounter along the way? Your experiences not only enrich the community, but also guide future enhancements. Stay tuned for upcoming episodes where we will explore the inner workings of the shader translation pipeline, interview some of the key maintainers behind the project, and examine how emerging hardware trends will influence the next wave of compatibility solutions. Until then, keep experimenting, keep sharing, and remember that the boundaries of technology are only as firm as we allow them to be.